Now we're ready to look at some applications of linear equations. So being able to write the equation of a line allows us to model these word problems, these real life applications that we have. If it follows a linear model, then we can use these linear equations to help us predict what y will be if we're given an x value. Okay, for example, we got two examples here that we'll look at. The first one, we're given a table that shows the average desirable weight for women of a given height. And this data is provided by a local health club. A woman who has a height of 60 inches should have a corresponding desirable weight of 108 pounds, right? 63 inches corresponds to 118 pounds, so on. In order to be able to use these linear models, we want to first make sure that our data follows a linear straight line pattern. And so what I've done here is I have graphed our data points, right? I've graphed 60, 108, 63, 118, and so on. And I drew a line through these 5 points. It's like a line of best fit that minimizes the errors between our estimation and the true value. And I've drawn this line so that it goes through exactly the first point and the last point. Okay, so this, and you can see visually that this does follow, in general, straight line pattern. Maybe not a perfect straight line pattern, but it does follow a straight line pattern to where we can get a good estimation. If we know the height of a woman, we can tell her what her average desirable weight should be according to this health club. All right, so the first thing we need to do is be able to write a linear model. Once we have that model, we can use that to predict. All right, so I've broken this down into a part A and a part B. All right, so part A, find a linear model using an equation that passes through the points corresponding to heights of 5 foot and 6 foot. Now the 5 foot, that's the 60 inches, the first point, and the 6 foot, that's 72 inches, that's the last point. Okay, so we're finding a linear model. In other words, we're trying to write the equation of a line that passes through these 2 points. All right, so we're going back to the examples that we had seen previously, to where we ask ourselves the question, do I know a point and a slope? All right, we know a point, we are not given the slope, but we should have enough information to find the slope. In this case, we do, because we know 2 points that this line passes through. It passes through the first point, 60, 108. And it also passes through that last point, 72, 152. All right, given that, given these 2 points, I can find the slope by subtracting the y values, 152 minus 108. And we're dividing by the difference in the x value, 72 minus 60, which is 152 minus 108 is 44. 72 minus 60 is 12, which will reduce down to 11/3. Now that I have the slope, I can find the equation of the line. I can use either point that I'm given. I'm just going to use that 60, 108 for my x1, y1. So y minus 108 equals the slope, 11/3, times x minus 60. Okay. And so if you like the approach that we took in the other examples, to where if we see a fraction, the very first thing we do is to multiply everything by that denominator in order to get rid of the fractions. Now, you don't have to do this. If you don't mind working with fractions, then just proceed with distributing that 11/3. But I find that most of us like to avoid fractions. So let's multiply by 3 at the very get-go, just to get rid of this fraction. And remember, we're multiplying by 3, so that on the right-hand side, that will cancel the denominator, leaving us with 11. times x minus 60. So distributing the 11, I'll do that in the same step. 11 times x is 11x. 11 times negative 60 is negative 660. Okay, and so now we'll write our linear model in slope-intercept form. All right, so we're solving for y, so we'll add 324 to both sides here. All right, so that will give us 3y equals 11x and negative 660 minus, let's see, plus 324 is a negative 336. And then we will divide both sides by 3. That leaves us with y equal 11/3 x minus 112. So this is our linear model. Y equal 11/3 x minus 112. So we can use this linear model that we have, all right, this linear equation to answer part B, right, where we're trying to estimate the weight given a particular height. Estimate the average desirable weight for a woman 5 foot 5 inches. Now, we do need to convert that to inches because that's what our data values are. It's given in inches. 5 foot 5 inches, 5 foot is 60 inches plus another 5, that's 65 inches, right? So our x is 65. So I can plug 65 into the linear model that I have and solve for y. That will give me the average desirable weight for a woman 65 inches tall. So I'm just plugging 65 into the x and simplifying. All right, so y equals 11/3 times 65 minus 112. 11/3 times 65. I'm going to say 11 times 65 is 715. So that's 715 over 3 minus 112. Now, it's fine for you to just plug that into the calculator. I will say, be careful with rounding. Not so important here, but it will be very important later on in the other chapters that we're looking at. Try to use exact values instead of rounding. Okay, so in an effort to show you how to use an exact value, we should get a common denominator. Right, we're subtracting 715 over 3 minus 112. Get a common denominator, which is 3. So I'm going to multiply 112 over 1, right? We can think of that as 112 over 1 by 3 over 3. All right, so that is 112 times 3, that's 336 over 3. Now I've got a common denominator, and I can subtract the two denominators here. That's 379 over 3, which is 126 1/3, right? Now the directions do not indicate how accurate that we need this or how precise that we need it. I'm going to leave this. I probably could round it to the nearest whole number here would be fine. I'm going to do that here. Since our data is in whole numbers, I'm going to leave my estimation, my final answer, as a whole number. It's 126.3 repeating, but let's just call that 126 pounds as my estimate for the average desirable weight for a woman who is 5 foot 5 inches. All right, so that's one example of how we can use linear equations for modeling. Okay, now let's look at another example. For this example, we're working with pending corporate fraud cases. The number of pending corporate fraud cases stood at 545 at the beginning of 2014, and it increased to 726 at the beginning of 2018. And it's observed that the growth was approximately linear. Now, this is just something that's given to us. We can assume this, and we need to assume in order to work the problem using the linear models. So the problem will need to tell us that it's approximately linear. All right, so part A, part B. Part A, derive an equation of a line to model the number of pending corporate fraud cases in any given year, right? So given the year, this linear model should tell us an estimate of the number of pending fraud cases. And part B, estimate the number of pending corporate fraud cases at the beginning of 2020. All right, so part A first, then we can answer part B. For part A, derive an equation, right? In other words, we're writing the equation of a line. Okay, in order to do that, we need what? A point and a slope. Okay, so are we given a point and a slope? We're not given anything explicitly, but we can draw what we need out of the problem. Okay, so maybe do some highlighting here. What are we given? Right, we were given that the number of pending corporate fraud cases was 545 at the beginning of 2014. Now, I'm going to use that for my first ordered pair. Okay, and instead of using 2014 as my X, because that's a really big number, I'm going to use that as my starting point. I'm going to say X equals 0 corresponds to 2014, and the number of cases at X equals 0 is 545. Let me make a note here. So 2014 corresponds to X equals 0. Right, and so that means 2015 would correspond to X equal 1, 2016 it would be X equal 2, so on. Okay, and I'm also given that at the beginning of 2018, the number of cases was 726. All right, so 2018 would correspond to what X value? Right, if 2014 was X equals 0, then 2018 would be X equal 4, right? That's 4 years later. And that has 726 for the number of cases. All right, so we've got 2 points, and that's all we're given, right? But drawing those 2 points out of the problem allows us to proceed with finding the equation of a line, right? We've got to know the slope, and since we've got 2 points, we can find the slope by subtracting the 2 y values. 726 minus 545 and subtracting the x values. 4 minus 0. $726 minus 545 is 181, and 4 minus 0 is 4. Okay, and that gives us, it'll give us a decimal. I'm going to write the slope as a decimal here, 45.25. All right, so I've got the slope, and I've got a point. I've got a special point here. Do you see the special point? All right, remember back from a previous video, we said that when the x value is 0, that is a special point. That is the y-intercept. That's a special point because if we have that y-intercept, then we can use the slope-intercept form and bypass that point-slope form, because we know that the b in y equal mx plus b is the y value that corresponds to the x value, x equals 0. So then we can say that y equals mx plus b, that the m is 45.25 x plus the b, which is 545. And this is our linear model that expresses the number of corporate fraud cases in terms of years, where the years correspond to the x values, right? X equals 0 corresponds to 2014. All right, so using that linear model, now we can answer part B. Estimate the number of pending corporate fraud cases at the beginning of 2020. So to do this, we need to know what the corresponding X value is. You can't plug 2020 into the X because we we changed the scale there, right? We had said that 2014 corresponds to x equals 0. So 2020, 6 years later, would correspond to x equals 6. So we'll plug 6 into our linear model. 45.25 times 6 plus 545. 45.25 times 6 is 271.5. Plus 545 is 816.5. And we're talking about the number of corporate fraud cases. We wouldn't leave that as a decimal. So let's round to the nearest whole number. We'll use conventional rounding. So that 0.5 is going to bring it up to 817. So assuming a linear model, that this growth is linear, we would estimate that the number of pending corporate fraud cases at the beginning of 2020 is 817.